Greetings. In this tutorial, we want to explain how NETFABB simulation determines whether the deformation of part geometry during a build is likely to interfere with the recoder blade. Parts displacing upward through the powder and being struck by the blade is a common cause of part failure during actual builds. After discussing this issue, we will run through an example of a simulation that will trigger a warning of recoder interference. NETFABB simulation works with a value of recoder clearance or tolerance, which is expressed as a percentage. Let's see how this works. In these diagrams, the gray block represents the solidified material of the part, and the blue area on top is the next powder layer. In the ideal case, with 100% tolerance, none of the previously deposited material has deflected upward into the powder layer. In the second example, an 85% tolerance means that the build has deflected up into 15% of the powder layer. This amount of deflection is normally acceptable. The default value for recoder tolerance in NETFABB simulation is 80%, and if the actual tolerance drops below this level, warnings are reported in the log files indicating that the part is getting too close to striking the recoder blade. That's what we see in this third diagram, where the build has deflected upward into 81% of the powder layer, leaving a tolerance or clearance of only 19%. Finally, an extreme case is shown in the fourth diagram, where the part has deflected up through the entire powder layer and 25% higher, producing a negative tolerance of minus 25%. The part in this case would definitely be hit by the recoder blade and possibly damage it. To see recoder interference in play, let's go to NETFABB simulation and open a suitable project file. Note the large overhang here that is very likely to deflect upward as it is built. Without making any changes to settings, we'll just click Solve. After the simulation results are loaded, check that we are seeing the displacement, then play through the progress of the build. As the build gets up above the overhang, we can see that the part is starting to deflect upwards. To better see the colors here, we can turn off the display of element edges. Let's check for warnings in the log files. Scroll to the bottom of the mechanical log, and we see 6 warnings and 1 critical warning listed. If we look at the Recoder Blade Interference tab, we see that in several of the layer groups, the clearance dropped below the default recoder tolerance setting of 80%. The most extreme was in layer group 6, where clearance was minus 2.7%, indicating a part deflection that extends up above the powder layer, so the part would be struck by the recoder blade. Note here that the time was 67.11 seconds. Back in the mechanical log, in the critical warning text, we can also see that the minimum clearance occurred at a build height of 12.48 millimeters. Either one of these facts can help us get to the critical part of the build animation. On the animation panel, we can step back to the 12.48 Z height and the 67.11 seconds mark. We can see that the greatest displacement occurred in the material deposited at the beginning of the overhang. If we switch to the temperature view, we can see that the entire overhang experienced the highest temperature. As a design engineer, you now have the evidence to suggest the need for a design change in this part. You could, for example, shorten the overhang if that dimension is not critical. Alternatively, you could add support structures to restrain the part from deflecting upward. After changing the design, you could rerun the simulation to see if the recoder interference issue was solved. If we want to make our simulations more sensitive to recoder blade interference, we can adjust the value for recoder tolerance. Go to the Home tab, click Solver Settings. You can see the default tolerance value of 80% here. And if you want a safer, more conservative value, increase it to, for example, 90%. Also note that you can check an option here to stop the analysis if recoder interference is detected. So just to review what we've done in this tutorial, we explained the concept of recoder clearance or tolerance and how it's measured. We ran an analysis that produced a recoder interference warning, and we saw how to find that point in the simulation.